Okay, so what is time-dependent density function theory? In the most straightforward sense, it could be regarded as a extension of its time-independent counterpart, which is the ground state DFT, wherein the Hornberg-Cohen theorem, which establishes a one-to-one correspondence between the ground state density and the potential, is superseded by the Runge-Gross theorem, which achieves a similar one-to-one correspondence between the time-evolving density and the external potential for a fixed initial state. So what TDDFT allows us to do is, using the Runge-Gross theorem, it allows us to write our observables in terms of as a functional of this density and the initial interacting wave function. So, and it allows us to map this interacting system onto a non-interacting system with an initial state chosen in such a way that it reproduces the density, the time evolving density, and its first time derivative at an initial stage. And because of the above property, because of the above expression, we can extract all the information of the interacting system from this non-interacting system, which leads to this following simplicity, that instead of having to solve the full n electron time-dependent Schrodinger equation, which has this complicated wave function, it allows us in real time TDDFT, one only needs to solve the n electron time-dependent Schrodinger equation that reproduces the density and the first derivative of the density with respect to time at initial time. So it allows us to do this by using this Kohn-Sham potential. By Kohn-Sham potential, I mean this one-body potential in which this Kohn-Sham system evolves, and it has, as you can see, it constitutes of three terms. One of the terms is the external potential, which would be the field of the nuclei or the external potential you might want to apply. Then there is the Hartree potential, which comes from the interaction of the electrons with one another. And finally, we have this with the XC potential, which will be the main focus of the rest of this talk. And so since the one-to-one mapping that we saw earlier holds for an initial state, and to be able to reproduce the density of the interacting system from this non-interacting system, this condition endows this VXC with functional dependence on the initial state of both the interacting system as well as the Kohn-Sham system. Furthermore, it also depends on the history of the density, which is referred to as the memory dependence, and it consequently leads to this highly complicated functional, which has this functional dependence on space and time in a non-local way. And so even though TDDFT allows us to do this nice transformation, but it doesn't come without its own difficulties. And one of the difficulties is that this functional is not known exactly, and it needs to be approximated to be able to apply TDDFT to real systems. So how are the approximations made? Well, one of the approximations is the so-called adiabatic approximation, in which the memory dependence, which is this non-local dependence on time, the non-local dependence on time, is completely ignored. And instead, an instantaneous density is inserted into the ground state approximation for the XC potential. So you completely ignore the memory. And most of the calculations that use TDDFT end up ignoring this memory. And so what are the consequences of ignoring the memory or using adiabatic approximations? Well, quantum mechanical dynamics is rarely adiabatic. In fact, most of the practical situations that we encounter are non-adiabatic. But surprisingly, the approximations are often quite accurate to be useful in real systems. But this lack of memory dependence does lead to errors in some predictions that we use that we make using the adiabatic time-dependent density function theory. So then one might then ask, one might then want to know, how does the adiabatic approximation compare with the exact Xc potential? And to do that, one usually solves the system, a real interacting system, and then compares the results with the approximations for the VXC. But such studies usually require two ingredients. One of them is you first need to solve the interacting system. You need to first solve the interacting system exactly. And then once you have the density, you can invert the time-dependent Kohn-Sham equation to find the exact potential. But these calculations are usually quite difficult to do for real systems, interacting systems. So by and large, these studies are limited to model systems involving one dimensions. Okay, here is one of the examples. So here we look at one of the examples of such a study. So we start with a 1D helium atom, with a one-dimensional helium atom, 2 electrons, and then solve the time-dependent Schrodinger equation for this, get the real density, get the eigenstates, and form our initial state as a superposition, 50-50 superposition of the first the ground state and the excited state, and consider the field-free dynamics of the superposition of this superposition state. And so we use, for the Kohn-Sham state, for the Kohn-Sham initial state, we use the single Slater determinant to reproduce the density and its a longitudinal component of the current. And here you can see that the adiabatic approximations like LDA and EXX, which is the exact exchange, when we do the exact exchange, it reproduces and timescales that are not correctly that don't correctly measure up to the real dynamics of the dipole oscillations. And the reason for that is there is a movie which shows the dynamics of the density, exact density, shown in black, and this one of the adiabatic approximations. And as you can see that in the Xc potential, there is this feature that is completely absent from the adiabatic approximations, which consequently leads to the wrong dynamics for the density and for the dipole oscillations. And even for adiabatic approximations that are adiabatically exact, meaning that once you account for the non-locality in space, even if you account for the non-locality in space, there are features that are completely absent from those approximations. So one of the questions that one can ask then is, do these features persist in 3 dimensions? And it's sometimes argued that correlation effects are stronger in the one-dimensional cases. So the natural question is to ask is, to what extent are these features the consequences of reduced dimensionality? In particular, do we want to know, do these non-adiabatic features that we saw in the one-dimensional, do these non-adiabatic features persist in case of a real 3D system? And if they do, can we find any dynamical property of the system that we can relate to these non-adiabatic structures? So to do that, the system we study here is a three-dimensional analog of the one-dimensional case that we considered previously, which is a 3D helium atom. And so we again consider its field-free superposition, which may be reached by applying some field that's turned off after some time. And again, like the last example, we first have to solve the Schrodinger equation for this system and obtain the eigenstates. And so to do that, we use this closed time-dependent closed coupling method, in which we make partial wave expansions in terms of coupled spherical harmonics, and use finite element discrete variable representation to discretize this radial degrees of freedom. And then once we have the solutions, once we have the eigenstates, we form a superposition of the ground state and the first excited state. where this A allows us to tune the amount of excited state we put into this superposition. So for A equal to 1 example would be the 3D analog of the example that we considered previously, which would be a 50-50 approximation. And if we want to go higher in terms of the fractional component of the first excited state, we could increase the value of A. So, and so then we want to find the Kohn-Sham potential, which reproduces the exact density of this interacting state that we consider, and its first time derivative at the initial state. So the density is given by this. And as we saw, the XC potential does depend on the initial choice of the Kohn-Sham state. And in principle, we can choose any Kohn-Sham state as long as it allows us to do what we show here. And so the choice we make is a Slater determinant. In fact, this is quite a natural choice here. If the state is reached from applying an external field to a ground state and then turning the field off, the Slater determinant is the natural choice in this case. In most of the physical situations where you have this ground state, you evolve it to this excited state. And then, since the Kohn-Sham evolution involves a 1D Hamiltonian, our state will remain in this single Slater Kohn-Sham determinant. And so our Kohn-Sham system then consists of this doubly occupied single orbital KS orbital, spatial orbital, in which is characterized by the density and the phase. And this phase is related to the current, to the longitudinal component of the current, through the equation of continuity. And so for this choice of the Kohn-Sham orbital, we can invert the Kohn-Sham equation analytically, and we get an expression like this, which consists of 3 terms. And so once we have this equation, one then needs to invert this equation to find alpha, and then once we have alpha, we can get the Kohn-Sham potential. And so it reduces to solving this equation for alpha. And looking at this equation, this resembles a Sturm-Liouville type equation, and has a unique solution for a given boundary condition. And also our initial state here has it's m equal to 0, so it has no azimuthal dependence, phi dependence. So it has an azimuthal symmetry in the density as well. So we effectively solve this equation in 2 dimensions with the following boundary conditions. And so we impose the boundary conditions that R goes to infinity at any time, large R, alpha is essentially 0, and to ensure that our alpha, the function alpha, is smooth across theta equal to pi and 0, we put the first derivative of alpha with respect to theta equal to 0. And then so one more thing that when we choose such a boundary condition, and at t equal to 0, it fixes the initial state for our Kohn-Sham orbital. So here, if we fix this t at t equal to 0, we fix this alpha, we get a unique Kohn-Sham orbital, and then Runge-Goer's theorem ensures that there is a unique exchange correlation potential that reproduces the density that we saw previously. And so we construct a matrix representation of this operator here, and then invert this equation to get alpha. And once we have the alpha, we can calculate a Vs from this equation right here. And then to extract XC potential, we use the following equation. Since the Hartree potential can be extracted numerically by inverting this equation. And for this choice of KS state, we already know that the Vx, the exchange potential, is minus half Hartree, and from which we can easily calculate the correlation potential. So finally, we extract the correlation potential in order to compare it with the one-dimensional cases. And so what's the result? The results, as you can see here, I'm showing here the plot of correlation potentials for different times. So t equals 0, t equals t over 8. This is t, this capital T is the period of the oscillations. And this goes from pi equal a little bit above pi by theta is a little bit above pi over 2 to a pi, which is the lower half plane of the xz plane. And you can immediately see that these features, as we saw in the previous case, in the 1D case, persisting in the 3D version as well. Moreover, even though we haven't compared these results, with the adiabatically approximated VC, the correlation potential, but the very fact that these features are similar in nature and similar in character to the one-dimensional case, it gives a pretty good confidence that these features are in fact adiabatic and non-adiabatic in nature. Moving on, so if we look at a particular theta, the snapshot of these components of VS, so this will be VHXC, artery exchange, and then there's VXC, exchange correlation, and then correlation. And we can see that in the region where the density is kind of mostly localized, so we almost see the VC is almost flat. So the force is coming from it's not as much as compared to the other ones. But once you get to the region where we have the minimum of the density, where the excited state kind of sort of starts dominating, we have the sharp peak. And then finally it levels down to this value here. So we again see the features, the peak and the step features that we saw appearing in the one-dimensional case. And and then we take different superpositions, as we saw that this A allows us to make different superpositions of our state. And so as you can see that for the finite values of A, so A equal to 1 would be the analog of our the 3D analog of our 1D case. You can see that it has a step, and these peak features are quite similar. And when we increase the amount of the as the fraction of the excited state is increased, the steps kind of decrease in magnitude. They decrease in magnitude, but spread over a larger region. And when you go all the way to here, all the way to A equal to infinity would be like totally excited state, and so it has to reproduce the structure in the density at all times. So you have this structure appearing at all times. Now here's a movie that shows the dynamics of the VC correlation potential. And you can see that this potential, this peak and this step feature is localized in the region where and at the time when the density has a minimum. So the function of it essentially is to keep this, to produce the right dynamics of the density and to keep this kind of separate, these two regions of the density separate. So what are some of the observations that we make are that if we look at the equation that we got when we inverted the time-dependent Kohn-Sham equation using the orbital, single slit or orbital W occupied, we got this expression. And from our analysis, we see that these peaks tend to arise from this term, the second term here, which is related to the local velocity in the density, local velocity in the system. And the steps seem to appear from this this third term. And if you take a radial integral of this term, so alpha dot, it gives you the size of the steps that you see in this here in this figure. And these steps in the VC we see that they are linked to the initial configuration of the Kohn-Sham system rather than the electron interaction. How do we know that? We did the same analysis for a non-interacting helium, like we chose the same initial configuration, except we turned off the interaction between the atoms, between the electrons, and we saw the similar structures appearing in the VCs. And so VC of the correlation potential of non-interacting helium atom displays steps of similar size, and but only the difference was that these peaks were sort of damped, suggesting that the barrier that we saw, which was acting as which was a consequence of the Coulombic interaction, are missing here, which is consistent with what we saw previously. And so then one might then ask how general all the results are. Is this a simplistic dynamics? Although we did consider a rather simplistic dynamics of a field-free evolution, but in fact the results apply for general cases in which there is this two electron system and it has this configuration. It doesn't matter how you got to this configuration, initial configuration, which is because of this exact condition, which states that any dependence of if you want to exceed potential for a state at any time t, that happens to be in any of these linear superposition, then the exceed potential that we found is directly applies no matter how the system got there. So you can either frame it as a dependence of initial states of the Kohn-Sham state, initial state of the interacting state, and the history of density up to that point, or you can similarly, or you can alternatively write it as a functional of the Kohn-Sham state and the interacting state at that time. Moving further, so one final question that we ask is, how closely does the Kohn-Sham current reproduce the exact current in this case that we consider? Now, it has been known in the context of TDDFT that the exact Kohn-Sham current could, in principle, differ from the true current by a rotational component. But the difference, how large the difference is for realistic systems is not usually known. So the first thing to notice is that the longitudinal component of the current, two currents, is the same thanks to the equation of continuity. But it only tells us part of the story. It only gives us the longitudinal component. It doesn't tell us anything about the rotational component. In fact, for our choice of the initial our choice of the Kohn-Sham state, you can write the Kohn-Sham current in terms of this alpha as n grad alpha, from which it immediately follows that the curl of Js over n must be equal to 0. Now, if the two currents were the same in this case, then one would expect that for the true current, this equation holds for the true current as well. In fact, some calculations do in fact assume that there is an equality between the true current and the Kohn-Sham current. So what they do is they directly calculate the true current from the Kohn-Sham orbital. So what we find is that in fact that's not true. The curl of J over n for the true current is not equal to 0. So here we see the longitudinal and rotational component of the true current. As you can see that for a equal 2 and a equal to 1, the longitudinal components are on top of each other. But there is a difference when it comes to the rotational components. They differ by some amount. And to make sure that these are not as a consequence of some numerical error, we compared the fractional differences in the curls and the longitudinal components. So the errors would be coming from numerical errors, but as you can see that they're negligible in comparison to the fractional difference that comes in the rotational component. It's only here that when the denominator becomes negligible, there is a divergence here. But in the region where the denominator is finite, you can see that the errors are negligible there. But in case of the rotational component, there is a substantial difference between the two. So in conclusion, the non-adiabatic features that we saw in the VXC exchange correlation that have been seen in the 1D systems previously appear in the real 3D systems with similar comparable magnitudes and are not just a consequence of reduced dimensionality. And so these results naturally inform the ongoing development of accurate functions for real-time calculations using TDDFT. And so we have also demonstrated for this system that the true current, in fact, does differ from its Kohn-Sham counterpart. And this difference depends on the relative proportion of the ground and the excited state that you put in the interacting in the configuration state. Thank you.